Section 4.4, Linear Correlation. Alright, in this section we're going to look at the linear correlation coefficient r, which is of n data points, and it's one of the square roots of r squared, which we just saw in the last section. We say one of the square roots because numbers like 9 have two square roots, a positive 3 and a negative 3. And sometimes correlation is positive and sometimes it's negative, so we want to allow for both those possibilities. And you'll hear sometimes in the news them talking about a study that they found that one variable is correlated to another. And when they're talking about that, some synonyms for what they mean, they might just be saying that those two things are related to one another, that they are connected, or maybe associated. So specifically in statistics, we would say that the linear correlation coefficient r is a number that measures the strength and direction of a linear pattern for our data set. So we're looking at data that's not just related, connected, or associated, but connected and related in a linear fashion. And the correlation is going to tell us how strong that connection it is and what direction it is in. So the best way to get a feel for this at first is just to go ahead and look at some examples. So let's go ahead and do that. If you have an r equal to 1, that's what we call perfect positive correlation. So the strength of the correlation or the pattern is that it's perfectly linear. You could draw a line through that would actually hit all those points. And the direction is positive, meaning that it's an upward pattern. And if you have a negative 1, you'd think if 1 is perfect, maybe negative 1 is terrible, but no, negative 1 is also perfect. It's just a negative correlation means that we have a downward direction to our pattern. But again, it's still perfect. You could draw a line through that would hit all those points. As your linear pattern starts to kind of loosen up where it wouldn't be perfect anymore, but it's still strong, your values of r will drop off from 1 and negative 1 a little bit towards 0, but we're still very close to 1, still very close to negative 1 because our pattern is still very strong. You might notice at this point that the positive r is like a positive slope and the negative values of r go with a negative slope, and we'll see when we see the formula that that is not a coincidence. If your pattern starts to loosen up a little bit more, where there's still definitely an upward trend here and it's as linear as it is anything, I don't see it curving, it's just not real strong or tight. If I drew a line in, the misses or the errors or residuals are getting a little bit bigger. And with that, we're falling away from 1 and down to 0.8. And our r here is down to negative 0.8. And this is, again, the same strength as that one. It's just a downward direction. And if we continue on to the next page, we can see that trend continuing to change as the pattern loosens up some more. And we get what's almost just a blob with an upward trend and a blob with a downward trend. We see our correlation weaken to 0.419 and negative 0.419. In fact, this might even be a surprise to you. When you first look at this, it might seem like it's just a random mess, but there is a little bit of an upward trend, but not a lot. And so you might think, well, wow, 0.4, that's like right in the middle between 0 and 1, or almost in the middle. But keep in mind from the last section that if r was 0.4, then r squared would be 0.16, and that means that linear regression is only removing about 16% of the squared prediction error. So overdoing that horizontal prediction line versus the one here that would be just a little bit of an upward slant, you get an improvement, but not a big improvement. So keep that in mind when you see an r that's kind of in the middle, like a 0.4, that think about that r squared number, which would become closer to 0. And the same thing for this one, just a negative pattern. And then r that is close to 0 is kind of an interesting case because that can mean a couple very different things. If you have just a complete mess with no pattern whatsoever and no upward or downward trends, you can get an r of 0. But here we have another r of 0, and yet you look at this and this is not a mess at all. It's a perfect pattern. It's just that it's a perfect parabolic or quadratic pattern instead of a linear one. And we need to always keep that in mind, that our value of r is the strength of the linear pattern. And so if our pattern is a shape other than linear, that is not necessarily going to measure up using this r. And so we can't fall to the conclusion that when r is 0 that there's no pattern to the data. We can say there's no linear pattern. There's not a linear pattern here. There's not a linear pattern here either. So just keep that in mind, that r equals 0 can mean two very different things. Alright, so we've seen a few different pictures, so now let's try our skill with that and look at this picture and think about that question of, well, what R is this? So I'd like you to take a guess at that. Maybe just pause the video for a second and try and make a guess for what R is, but just a little bit of advice as you go to do that. Use the pictures that you've just seen. Maybe look back over the last page and this page and try and figure out where this fits in. You're not going to find it perfectly, so you're probably going to want to guess in between two of the values you've seen, and I would suggest just guessing to 1 decimal place. So go ahead and pause the video and take a quick guess there. Alright, so let me go ahead and show you the strategy I would use for guessing on this. The first thing that I notice is that this pattern is a downward pattern, and that means I'm going to guess something negative. It's not perfect, so it's going to be a decimal value. So negative 0 point something. So when I start looking at the ones that I have, I can look at this 0.419, and I can say, you know what, my pattern is not that bad. And I can look at the negative 0.806 and say my pattern is not that good. And in fact, I would say that the pattern is closer to this one than that one. So if I was going to guess to just 1 decimal place, I would say, well, it's not this good, it's not nearly that bad, so let me go just a little bit worse than this and guess like R is approximately negative 0.7. So that's what I think I would put there if I was just going to guess to 1 decimal place. If you had any guess that was between negative 0.8 and negative 0.4, I'd say you did a decent job of narrowing it down to the right range, and you shouldn't worry too much that if you didn't guess the exact same number. A negative 0.6, a negative 0.5 would also be good guesses as well. Just wrapping up that last example, it turns out that that one that I made a guess of negative 0.7, if you put that into Minitab, StatCrunch, into the calculator, something that could compute that correlation for you, it turns out that it's negative 0.729. So my guess was close. If your guess was negative 0.6, again, I would say that's close. You shouldn't feel bad about that at all. And you'll find that as you do more and more guessing, you get better and better at that. And we'll practice that when we get to our tech project. So don't worry about it if you're not real good at that right now, but it is something that we do want to try and continue to get better at. So we're going to go ahead and talk about how we interpret R in terms of different applications that we're working on. And I want to start out by just showing you the formula. Now the formula is quite messy, and don't be alarmed by that because we're actually going to use the calculator to calculate R every time that we do it. But the one thing that I wanted you to notice here, and it's just a quick mention, is that the denominator of this is positive. And if you were to look back at the denominator of our slope calculation, it was always positive. And the numerators of the two are the same. And so just the quick kind of takeaway from that is that this value of R and the value of slope are always going to have the same sign. So that thing that we saw in the pictures where the ones that were going upward had a positive correlation, just like the slope, is not a coincidence. The ones that were going down had a negative correlation, just like the slope. That's also not a coincidence. So when we go to interpret R, a few things to keep in mind. R is always going to be somewhere between negative 1 and 1. And remember, those are perfect correlations, both of them, one perfect positive, one perfect negative. And if R is close to 1, then there's a strong positive linear correlation between the variables. And if R is close to negative 1, then there's a strong negative linear correlation between the variables. And it's from those two lines that we get most of our interpretations. And just to kind of help you out a little bit here for homework and tests and collaboratives and stuff, when I ask people to interpret these, I expect them to say there's a strong positive, and I'm looking for that, but I'm also looking for the words linear and correlation. And also when you get to the variables part right here, you would want to specify what those variables were. So you'll see in a minute for the Mustangs, we'll talk about the age and the price, but you wouldn't just say a generic variables, you would mention what the variables were in the problem. And then the other thing that can come up as well is R might be close to 0, and then we would say the variables have weak, if any, linear correlation. But just a caution there, we saw this in the pictures. If R is close to 0, that doesn't mean that there's not any correlation at all. It means there's not linear correlation. Remember our kind of U-shaped parabolic data that has a perfect correlation, just not a linear correlation. Okay, now that we've looked at the theory for R, let's go ahead and try and apply that to the example that we've been looking at throughout Chapter 4, and that would be the Mustang data. So quick reminder of that data set, and then we'll jump in. So we're looking at the age and price data for Mustangs, and we have a scatter plot for that data shown. The vertical and horizontal lines that are drawn in represent the mean of the X values and the Y values. So this vertical line right here is the mean age of the cars, so about 4-point-something years. And this horizontal line is the mean price of those cars, so that looks like around 18, which would be about 18, or 180, which would be about $18,000 roughly. And we'll make use of those later. The first thing we're asked to do here is to take a guess at the value of R. And that's something we just did with a generic picture a moment ago, and now we want to try and do that again with our Mustang. So just trying to look at the strength of that linear pattern. So kind of imagine drawing a line through there and how good of a fit is it to that data pattern. Well, the first thing I would notice with this is that it's a downward pattern from left to right, which means that our correlation should be negative. It's certainly not a perfect linear pattern, so it's not going to be as good as -1. Comparing it to this one, I don't think it's this strong, so I would say 0.978 is too big of a number to use. I think the pattern that we're looking at here, though, is probably better than this one, which is a -0.86. So I'd probably guess something in the middle and just go with something nice. So my guess at R is going to be that R is approximately -0.9. Negative because of the downward pattern, and then not quite this good of a pattern, not quite that bad, so I just kind of went in the middle. And we'll use the calculator in a bit to see what the actual number is and see how good of a job we did. And that, by the way, is why we've been given the sum of the xy's right here. That's going to help us check data entry on the calculator in a little while. Okay, let's go ahead and move on to part B. What percentage of the cars are clearly making a negative contribution to the linear correlation? Use the horizontal and vertical mean lines shown in the scatter plot to explain. So we know that we've got a downward pattern here, and that's why we're guessing that R is negative. But does every point contribute to that negative, or some of them kind of contributing contrary to that? So to explore that, we want to look at a different formula for R. This is the one we already talked about that kind of shows us it matches the slope, and we can tell that we're always going to have an upward line producing a positive R and a downward line producing a negative R. This one helps us to see these contributions. So very different looking formula, but algebraically it can be shown that these two are equivalent to each other. And this one kind of takes it one point at a time and says if you take an ordered pair and you find the z-score for the x value and the z-score for the y value, and you multiply those together, and you do that for all the ordered pairs and add up those products and divide by 1 less than the number of ordered pairs, you'll get R. So a very different looking approach, but it produces the same number. Now, so let's think about how does this end up being a positive or negative contribution. So each product is the contribution being made by an individual ordered pair. So we need to think, when would the product of the z's be positive and when would it be negative? So that's where these lines come in handy. This horizontal line right here is the average y value, y bar. This vertical one is the average x value, so that's drawn in at x bar. If you have an ordered pair that's over here in the upper right of those two lines, then because it's above average for x, it would have a positive z-score for its x value. Because it's above average for y, you'd have a positive z-score for the y value, and then the product of those two z's, so the zx times the zy, would produce a positive output in this quadrant. If you drop down here to the lower left, because you're below average for x and below average for y, you would have both of these turn out negative, but you would still end up with zx times zy equaling a positive. It would be a negative times a negative, but it would end up being positive overall. So it turns out that any ordered pair that is to the upper right of the mean lines or the lower left of the mean lines is producing a positive contribution to the correlation. So that guy right there is producing a positive contribution rather than a negative. Now we were asked to count the negative ones, so let me go ahead and look at that with you real quick. Why would these two be negative? Because it turns out they are. Well, the z-score for x, you're above that, meaning to the right, so you'd have a positive z-score for x here. So let's write out that product, zx times zy here. Because you're above average for the x, the z-score for the x would be positive. But you're below average for the y because you're below this horizontal, so that would be a negative. So overall, you would get a negative there, and that's true about anything to the lower right of those mean lines. And over here, it's just the reverse. The z is of the x's is to the left, and the z for the y's, you would want to note that you're above. So being to the left produces a z-score that's negative for the x value. Being up produced a z-score that's positive for the y value, and then the product ends up being negative, and that's true for all of the points there. So they wanted to know what percentage contributed a negative amount to the correlation. That would be any of the points that are in the upper left where we get negative contributions, or anything to the lower right where we get negative. So let me just switch colors and count those up. There's two values here, so I'll draw two circles. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And I feel like I might have missed one there. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 cars there. Okay, this is a little bit hard to see, so we're going to have to look at the data. I seem to have a missing car, right? Well, there's 3 that are 5 years old, and I only see 2 here. Notice these 2 have prices that are super similar to each other, so that's right here. That's actually 1, and I'm just going to circle it again. That's 2 cars. So when we count all the ones that have a negative contribution, it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Just like these 2 are really close when we're touching, those 2 are so close they're one on top of each other. So how many of the cars gave a negative contribution? All but this one. There were 12 cars there. So all but one means 11 out of 12. So 11 out of 12. And as a decimal, let's see what that would be. So 11 out of 12 is 0.9167. So 91.67% of the cars have a negative contribution to the correlation. So it kind of makes sense that we're guessing a negative correlation when the overall pattern of the data is 11 out of 12 of them making a negative contribution and only 1 making a positive contribution. So quick answer to that again, when you're asked this question, if you want to see a car that's clearly making a positive contribution, that's upper right or lower left of the mean lines, where the products are positive because of either 2 positive z's or 2 negative z's. A negative contribution comes from the upper left or the lower right, where you have the z-scores have opposite signs and you get a negative overall contribution. So in this case, that's 11 out of 12, or about 91.67%. All right, so continuing on, we made our guess at R that it was about negative 0.9. We looked at the contribution, saw that 91.67% of the cars were making a negative contribution to the correlation, but we haven't actually calculated the correlation yet. And we could use those formulas, but that gets to be a bit of a long, tedious job. So the other option would be to bring in the calculator and enter all the data. So go to Stat and Edit and enter the X and Y values. I have those in there already from the previous pages. If you don't, maybe pause real quick and enter them in so you can follow along. And then we're actually just going to do the exact same work that we did in section 4.3 to get R squared. We're going to hit Stat, Calc, and go down to number 8, which is linear regression, A plus BX, and tell it that our data is in L1, comma L2, and we get all this output that we saw before, our intercept, our slope, the R squared, and now the R that we're going to use. So I see now that our guess was pretty good. We had guessed that R was negative 0.9 and R is negative 0.8844. So that's a pretty good guess, definitely in the neighborhood where we were. The other thing that I just want to show you real quick is checking the data entry. So one of the numbers that they gave us with the data set was this sum of the xy's as 8492. So it'd be nice to check that to make sure it matches, to know I didn't make any mistakes when I put the data in. To do that, you go to the Stat menu again, go to Calc, and choose 2 variable statistics. Press Enter and put in the L1, L2 to let it know where the data is. And you won't see it on the initial screen, but if you scroll down, it'll go the mean and standard deviation of the x's, mean and standard deviation of the y values, and once you get past that, you get the product of the xy's, 8492. A little bit of a pain to find, but if you verify that that matches, then you can be confident you put your data in correctly, and that should add to your trust in the value of R that you're getting. All right, and then next we want to interpret R in terms of the linear relationship between the variables. So that value of R, negative 0.8844, is pretty close to negative 1. So I would say that there's a strong, because it's pretty close to negative 1, negative, because it's negative, linear correlation between the variables. And we said earlier you should always specify the variables. So I would say between the age and price. And maybe just for clarity, say between the age and price for the Mustangs. All right, and so that is a pretty strong negative linear correlation, being pretty close to negative 1. But even then, we have to be careful that we don't go too far with our statement about the connection between age and price. Even if things have a strong correlation, that does not prove that it's a cause and effect relationship. So correlation does not prove that you've found the cause. So one of the things I'd like you to think about is what else could be causing older cars to cost less. You might pause for just a moment and say, besides a car getting older, what makes it go down in value? So I would say that one of the things that does that, maybe even the primary one, is something called wear and tear. So wear and tear is just the idea that an item is getting used up. And it takes two things for an item to get used up: time and mileage or use. So I would say that one of the things that would point towards wear and tear is if a car had a lot of mileage on it. So if you put miles on a car, it's going to start wearing out the engine, wearing out the tires, wearing out the brakes. That's going to cause the car to go down in value. Age can do it too, because if you leave the car sitting out just outside for several years, the sun is going to start to damage it. Even just the air and moisture and all that stuff might start breaking it down. Even then, it's the sun that's causing the damage, not the age. It's the moisture in the air that's causing the damage, not the age. So there's lots of factors that can cause this wear and tear, which cause the car to go down in value. And when we start bringing up other things like mileage, sun damage, things like that, then we're starting to talk about working variables. And a working variable is a variable that is not included in the study, but that affects the variable being studied. So when we started this problem, we said, hey, let's look at the connection between age and price, and we found a strong negative linear connection. But that negative linear connection isn't necessarily the whole story. There's other working variables like mileage, like sun damage, which cause wear and tear on the car and cause people to value it less. So let me show you an example of how that idea works. It turns out that if you do the research on this, you'll find that there's a strong positive linear correlation between the number of Taco Bells a city has and the number of public restrooms it has. So in other words, cities with a lot of Taco Bells have a lot of public restrooms. When a city has less Taco Bells, it tends to have less public restrooms. So does this show that Taco Bell restaurants are creating the need or causing the need for more public restrooms? And if not, what working variable is a better explanation for this relationship? So if we went out and we looked, did some online research, looked up several different cities, counted how many Taco Bells are there, how many public restrooms are there, we'll see there's a strong positive linear correlation between them. But I would still argue that it's not the Taco Bells causing the need for the public restrooms. There's a working variable there, which is affecting both of these and making them look connected to each other. And if you think about what that would be, it's probably population. So here's our variable down here lurking beneath what we were studying. We did a study on Taco Bell versus public restrooms, and we saw a connection. But really what's happening is bigger cities have more Taco Bells and more public restrooms. Smaller cities have less Taco Bells and less public restrooms. So it's probably the population that drives the number of Taco Bells and the population that drives the number of public restrooms. But because it's driving both of them, we see them moving up when the population goes up, and we see them moving down together when the population goes down, and it makes them look like they're connected directly to each other, when really it's this working variable of population. All right, that wraps up section 4.4.